In this lesson, we're going to go through deformation, and you can see that according to syllabus, this is topic number 6. You can find other topics in the rest of my channel as well. The whole A-level syllabus is going to be covered in this one, A1 and A2 separately. So the first one, it tries to tell you that deformation is caused by tensile and compressive forces. Now, what is a tensile force and what is a compressive force? So if we go to this animation shared from PSC Colorado, so if you try to stretch a spring, this will be considered as tensile force. If you try to compress a string, this will be called as a compressive force. Now, why do we need to understand these words? Is because there are some materials that show strength when they are pulled, and some show strength when they are compressed or when some load is put onto them. So cement that we use for our houses and buildings is a good example of a material that shows compressive strength. Now you can load up cement with a lot of weight and you can see very tall buildings actually made out of this material. So you can put a lot of weight on this material and it will not shatter, it will not get destroyed in the process. But if you try to pull apart a piece of cement or a cement block, it will immediately turn to dust. So cement is a material that shows compressive strength but not tensile strength. On the other hand, if we go towards carbon fiber or carbon fiber material or even steel wires, right? So they show strength when they are pulled apart. So for example, in this situation, if you pull this spring or if you pull that carbon fiber or that wire of steel, they will show you a lot of strength and they will resist that and they will resist breaking. So carbon fiber actually shows us tensile strength. So just getting familiar with these words is more important. That's it. Remembering what materials do this and what materials do not is just a part of this lesson as an example. Otherwise, it's your choice. If you are interested in this, you can research this online as well. Then we have to understand the term load, extension, compression, and limit proportionality. This is exactly from O levels, what we've already done. So in O levels, what we do is that if we have a graph with force and extension, let's say extension is in millimeters, we say that according to Hooke's law suggests that force is proportional to extension. The higher the force, the more extension there will be, and we can see this in animation as well. If I increase the amount of force, the displacement over here also increases. So if I keep increasing the force, it keeps increasing. So that is what this law says, okay? But of course, provided that there are some limitations to this rule. And the first limitation is that the limit of proportionality is not exceeded. Now, what is limit of proportionality? We'll get to that later. So to conclude, F is equal to KE. In this scenario, we can see that K is equal to force over extension. If you do the unitary analysis, this will become newtons per millimeter. So the spring constant unit is newtons per millimeter. If this unit was in centimeters, then this would simply become newtons per centimeter. Does not matter. So what is the purpose of a spring constant? This spring constant actually tells you which spring in the real life is going to be stiffer and which one is going to be softer. That's it. So if you have a spring of value, let's say 50 newtons per millimeter, and if I have a spring of value K2 of 150, let's say newtons per millimeter, what does that mean? It means that this spring will require 50 newtons to extend 1 millimeter, and this spring will require 150 newtons to extend by 1 millimeter. So of course, this requires a higher force than this one. So K2 is going to be a stiffer spring, difficult to stretch, difficult to compress, and K1 will be a softer spring in comparison to K2. So spring constant actually tells you about this value in terms of real life. Now force is given to us in newtons. Now let's plot this F equals to KE. Now notice that this is a direct proportionality. So if we have F equals to KE, then this is compared with Y equals to mx plus C. Now since this is a direct proportionality, there will be no y-intercept, and this line is going to pass from the origin. And there comes a time when this proportionality ceases to exist, and after that point, the line actually turns to one side. Now, in case of a spring and in case of a wire, the line takes a different turn. So in case of a spring, the line is going to turn this way. Again, be reminded that this is for a spring. Okay? All right. So what's happening at this point? So this is a special point over here that is known as the limit of proportionality. I'm just revising O-level things. Okay, so this is the limit of proportionality. What does that mean? Is that a physical problem with the spring or is that a mathematical problem? This is a mathematical idea. So from this section to this section, the line is straight. So we can use F equals to KE. We are able to use F equals to KE, and because of this idea, we say that after this point, this is that last critical point, this is that last limit after which we see that the line actually turns or makes a curve, which means that the line is no longer straight, which means that the limit of proportionality has been breached. The system no longer follows F equals to KE. It no longer functions this way. So only in this elastic region, we can successfully use Hooke's law. That's why he will always mention in some question that limit of proportionality is not breached, is not exceeded, which means that you can use Hooke's law. That's it. Now, we have looked at the first 2 points. We have also looked at Hooke's law. We've also looked at spring constant. Then we move towards the actual A levels part. Now let's look at the extension. Extension would simply mean that if this is our spring, let's say, in the original unloaded condition, there is no force on the spring. So this is actually the original length. Let's call this L naught, original length, unstretched. Now let's say you put on some load on the spring and the spring stretches. So let's say that you've applied a force of 100 newtons, and let's call this length as L1. This is L1. So compared to the original point at the standard point, or this point right now, we can call this as extension E. In some books, you will find this variable as X. It does not matter. So extension or X is equal to L1 minus L0. So that is what we're writing down in Hooke's law formula, that the change in length is caused by the application of force. So if you open up this formula, this actually looks like this. Change in force is equal to K times change in length. This becomes F2 minus F1 equals to K times L2 minus L1. And be advised that one of the forces, current forces, will be for this length, and an initial force will be for this length. So in this case, since the original force was non-ended, was not existing, it was 0 newtons. That's why this actually is F minus 0 equals to K times L1 minus L0. So this becomes simply F equals to K times extension. That is how the formula actually narrows down to this idea. So we understand what is extension, how to visualize it. Now let's move towards stress, strain, and Young modulus. Now, in terms of stress and strain and Young's modulus, what we need to understand is this, that stress, simply put, is force per unit area. What does this quantity tell you? Now, if you look closely, if you inspect it, we realize that this is actually a unit of pressure, which is newtons per meter squared. But what does this tell us in terms of compression and tensile strength of a rod, of a string, of a fiber? What does it tell us? It tells us that how much force, for example, if this is a strand of, let's say, steel or a column of steel, how much pulling force or how much compressing force, it goes both ways. This force goes both ways. How much force it can sustain if it has a cross-sectional area of this much. And of course, we know that if we want to increase the strength of any material, what we do generally, we increase its thickness, we increase its girth. So what does that do now? It is now able to hold on to higher weights. It can now provide more tensile force. It can now sustain more tensile force. That is what we do in suspension bridges. That is what we do in large buildings. We start making their columns thicker, because we know that if we increase the surface area or the cross-sectional area, it is going to become stronger, right? So this is how you visualize stress, okay? How much force it can sustain on a given area, and it does not break, okay? So similarly, then we move on to strain. What is strain telling you? So now strain is basically a ratio of the change of shape. It only tries to tell you how much shape has changed or how much length has increased in compared to the original length. So this becomes actually x divided by L. In some books you will find change in length divided by length. In some books you will find extension divided by length. What does that mean? It means that if the object is very rigid, if it is a very, very solid object, then compared to the original position, let's say this is the original strand, and the current strand, if it is very rigid, let's say, I'm exaggerating the situation right now to understand it fully, the original and final length will have a very small value of extension because it's very rigid. It does not want to extend. It does not want to change its shape. So this is the original length. So when you want to find strain, when you want to find this, what you do is you find this extension, simply extension divided by original length. So how much has the shape changed as compared to the original length? So for a very rigid object, for a solid object, the value will be very small. Why? Because the extension will be small and it would not like to change its shape as compared to the original length. It would like to retain, it would like to maintain its shape. So strain is basically, simply put, change of shape. How much has it changed? On the other hand, it does not have a unit. Why? Because extension will also be in centimeters and length will also be in centimeters. And these are both lengths. That's why there will be no unit. Even if it is millimeters, over here, this will also be millimeters. If it is in meters, this will be meters. Doesn't matter. The unit will be cancelled out. Similarly, on the other hand, if you look at a rubber band, that is an example, right? If you look at a rubber band, this is its original length, for example, L. And if we apply just a little bit of force, we can see very clearly that the rubber band likes to stretch. It stretches a lot, right? So in comparison to the current situation to the next situation, this will be extension. Notice one thing, please be advised that this final length has nothing to do in any part of the system. This has nothing to do in any calculation. We always compare it with the original length and the current extension. Of course, if you have this length, you can find out L1 minus L to be the extension, but this will not participate in mathematics in any equation. We are only interested how much has it changed, how much has it stretched due to this application of force, for example, in both cases, if its original length is this. So for a rubber band, this value will be very high because it stretches a lot, right? So we understand now that what strain physically means, what you need to visualize when you look at strain. And over here, we understand what we need to visualize when we look at stress, okay? So let's try to solve some questions and see how we're going to use this formula. One more thing left over here. We have the formula for Young's modulus. Now, Young's modulus is actually just a ratio of stress divided by strain, which is going to be force over area divided by change in length divided by original length. If you simplify this algebraically, this is going to become FL over AX. X being the extension. Of course, we know from algebra this is going to come up, and this is going A is going to come down and get multiplied with X. Okay, so this is what it comes down to, FL AX. It just gives you a ratio between stress and strain, how much it can sustain the force up for that respective area, and how much will it change the shape. Okay, this is what the understanding of Young's modulus will be. Okay, so let's look at the question. It tells you that the wire is stretched by 8 millimeters by a force of 60 newtons. So what I would advise you to write down the original Young's modulus as FL over AE or AX, right? So what force you apply at 60 newtons? So let's make this as 60 multiplied by a length divided by the cross-sectional area is not given. So let's keep that variable as A into 8 millimeters, which was the extension X or E in any variable format. So over here, this is our original Young's modulus. And if he says that it is made out of same material, now notice that when he says same material, that means that the Young's modulus will not change throughout the question. Even if it is, let's say, even if you change the dimensions, the Young's modulus will not change. Because if you change the force, you change the length, you change the area, you change cross-sectional area, or you change the extension as well, whatever happens, these new dimensions will respond in such a way that it will give you the same answer for Young's modulus. That is a main clue, but you can say that is a main helping point, you can say, that actually enables you to solve the questions, because if the material is same, the Young modulus will not change. Now, in new situation, let's make the Young modulus again. He says that the material is same and the cross-section area is 4 times, so I will write down 4A and twice the original length, so I will write down 2L in the new situation. So if the force is same, when the same load is applied, which means that 60 Newton is still being applied, length is now double, because this is what he says in the question. Cross-sectional area has been increased by 4 times, and the extension is what we need to find out under these circumstances. What will happen now? So I know that the old Young's modulus and the new Young's modulus, they have to be same, right? So I'm going to equate them both. So what happens right now is that FL divided by AE was the standard ratio compared with the new situation. I'm not replacing force with 60 because I know it's going to be the same for both of them. This is 2L divided by 4 times the cross-section area multiplied by extension. Now this is E dash. This is what we want to find out. We can see very clearly over here that this FL and this F and L gets cancelled out. This cross-sectional area A gets cancelled out. So what we are left with is a simple cross multiplication. So this gets over here, this gets over there. So we are left with 4e dash is equal to 2 times e, right? So we know that the original extension, this was given to us as 8 millimeters, right? So let's replace that. So e dash is equal to 2 times into 8 divided by this 4. This comes out as 4 millimeters. So the answer of this question is option B. Okay. You can also try the ratio method as well, that if, let's say, force was not changed, length was increased, cross-sectional area was decreased, then what should happen to the extension? That's your choice. You can do it that way as well, but I'm going to show that method that is actually foolproof. Anyone can understand this. Let's move to the next question. Now, this is a good question in terms of one trick that I'm going to teach you. Now, the trick to solving these questions, in which he asks you about extension, in which he asks you about other things, this trick is to make a standard case. Now make a standard case of the spring and think about it this way, that if you applied a force X, it would have stretched by a value of E. That means that F is equal to KE and K is equal to F over E. Now I have the spring constant of the spring which is being used in these situations. So if the springs are identical, then the spring constant will also be the same. Now we know that in parallel configuration, the spring constants get added together. Why? Because in this situation, the springs are going to be difficult to stretch. Why? Because this weight is being equally divided among 3 springs. So either visualize a single spring with W by 3 force, because weight is divided in 3 parts, or add the spring constant together. Now, if this was a series combination, we have a series combination in the question over here as well. So don't worry about that. We'll discuss that later as well. So in parallel configuration, the spring constant get added together. Okay. So over here, what's happening is that for this current situation, we have F equals to Kx. And he mentioned that this is the extension. So F is actually W. K is going to be 3 times K and extension is X. So K comes out as W divided by 3X. Okay. So I know that one of the spring constant is going to be W divided by 3X. And you can see that there is a divided factor by 3, which means that W divided by 3 then multiplied by 1 over X, which means that the weight is being divided on 3 parts. However you visualize this, it does not matter. Okay. Now he tells you that the new situation in which one spring has been removed, the middle spring has been removed, and the weight has been increased to 2W. What to do now? No problem. So what you can do is, now you can visualize 2 springs like this and apply 2W. Now, we know that the springs in parallel get added together, or the spring constants get added together. So the new situation, it will be F equals to Kx, right? So this is what we want to find out. Let's keep it that way. So force has now been increased to 2W. So let's replace 2W. K on the original spring was W by 3X. Okay, so let's replace W by 3X. And notice that we have 2 springs, 1 and 2. So I will multiply this with 2 because spring constant get added together. So this was W by 3X. This was W by 3X. If you add them together collectively, most definitely that will become W by 3X plus W by 3X, which can be written down as 2W by 3X. Algebra simply, okay? Plus the extension which X dash, which we want to find out, we don't know what that is. Now you can see that W gets cancelled out, 2 gets cancelled out, and we're left with 3X. Let's take it over there. This becomes 3X equals to X dash. So the answer is going to be 3X. The extension will be 3 times. So always make a standard case and then compare it with the rest of the situation. Okay. Now let's do the same thing over here. In a series combination, what is a series combination? In a series combination, the spring constants get solved like this. 1 over K1 plus 1 over K2 equals to 1 over K total. Now generally what this looks like is that the overall spring constant is going to get reduced. It's going to get decreased. Okay. So let's try to compare this in this situation. Again, make a standard case and then start solving the situation. So the standard case very simply is going to look like this, that you're applying a force of F. It is going to cause an extension of X. Now let's start with this one. Now over here, I realize that the force or the load is being divided equally on both sides. So, or another way to look at this would be that if you have F equals to Kx, then you have to adjust K and X in new situation in such a way that the load becomes same, because notice That is the same load for everyone. If it's a force of 30 newtons, it's same for everything. So that means that I have to make F equally constant. So what does this equation look like? So equation will become something like this. F equals to K into X. Now, how much extension will there be? Since the load is being divided into two springs, I know that the extension is going to be halved. So what's going to happen to the spring constant? Spring constant will be doubled. As I mentioned earlier, in parallel, the spring constants get added together, and we can see that over here. This is becoming 2K as K plus K. Now, why did we do it? Why did we do this? First, we have to figure out the extension mentally, right? That the load is being divided. So if a single spring can stretch up to X due to this load F, then two springs experiencing half the force will stretch by half the value. So if this is stretching by X by 2, this is also stretching by X by 2. Collectively, they're moving downwards. Let me show you a visualization for this one. Let's say there are two springs like this. So if you pull them down, the stretching for both of them is exactly the same. They're going to stretch by same amount. It does not matter. Okay? All right. Sorry. So on the other hand, if we move toward this part, the load is same. I realize that it is going to be divided into two branches over here and over here. I realize that this is going to be X by 2. This is going to be X by 2. Now, since these springs are connected in series with each other, this comes down by X by 2. This comes down by X by 2. So the total displacement moved from the starting position to this new position will be X by 2 plus X by 2, which is going to be X. And if you want to calculate the spring constant in this situation, it will be overall total will be actually K. How did we get this? So what we target, the target is to make F equals to Kx. So F is equal to what should be the variable of K if the extension is X. Now, luckily over here, the extension was already 1. So the K spring constant will also be 1. And a shortcut of this is to make the reciprocal of the extension. I'll show you that, how is that going to look like. So in this case, the extension is X by 2. Over here, the extension is X, right? Because this load is experienced by a single spring, so we know that a single spring extends by X. And the load is being divided half and half on these two. So each of them is going to stretch by X by 2, and this is going to be X by 2. So collectively, this situation moves by X by 2. So notice what I'm going to do, how to find the spring constant in this situation. So F is equal to K times X. We don't know what's going to happen here, right? So I need to make sure that the load F is exactly the same because it's the same in all options. I figured out that the extension in this case is going to be X by 2 plus X, which becomes 3 by 2. Now, simply, if you want to make sure that load remains same, what should I put over here? What should I do at this situation? What variable should I use? I will use the reciprocal of this. This is why I said reciprocal before. So reciprocal of this will enable that this gets cancelled out with this one, this cancels out with this one, and we are left with F equals to Kx. That is the standard case that we started with. So that is how you predict. That is how you use this trick. Okay. Now it says what is the largest extension, what is the smallest one. So we realize this is actually 0.5x, this is x, this is 1.5x. So smallest is x, then y, and then z. It's already arranged in option A. Moving on to this question. Now this is where this trick is going to help us. Okay. So let's assume for this question that there is a single spring. We have a single spring that has a spring constant of 1. What would that mean? The spring constant of 1. It means 1 newtons per millimeter, right? So in this situation, we are assuming that there is a single spring, right? And we know that the spring constant is going to be this one. So we're keeping it as a unitary method, 1 newton for 1 millimeters. It will make things simple. So in this case, we can realize that in the option A, he asks us the largest extension. Let's figure out for everyone so that we understand how to use the trick of the standard F equals to Kx. Now, we know that our springs are identical, and I know that it's going to extend by 1 millimeter for 1 newton. So if 2 newtons is applied, this is going to stretch by 2 millimeters. This will stretch by 2 millimeters because this weight is experienced by both of them. So in series, every spring stretches. In parallel, although they do stretch, but they do stretch collectively and while the load is divided half on each of them. Okay, so be careful of that. So I can experience that this will be actually a 4 millimeter extension combined from the starting point to this point. Okay. All right, moving to this point, we have 1 newtons of force. I realize that 1 newton only stretches 1 millimeter. So this will be stretching by 1 millimeter. This will be stretching by 1 millimeter. This will also be 1 millimeter. So from the starting point to this current position, it would have stretched by 3 millimeters collectively. Okay, so this option is 3 millimeters. We move to the next one, 6 newtons divided by half on both springs. So I can say that a single individual spring is only observing 3 newtons of force. Now I know that my spring stretches by 1 millimeters if I apply a force of 1 newton. So this 3 newtons, so this will be stretching by 3 millimeters, this will also be stretching by 3 millimeters, and collectively, since they're moving together, it would make no difference as one extension will be equal to the extension of the other as shown in this example. It does not matter. Both are stretching by same value, right? Okay. So this is actually 3 millimeters, our answer. Last part, we have 8 Newton being divided into 3 parts, right? So what I can do is I can compare this one situation or one spring in this situation that comes out as 8 by 3. Why am I dividing this 8 by 3? Because this 8 Newton is dividing into 3 springs. So I have applied a Newton force of 8 by 3, which is actually 2.67 Newtons. Now what I have chosen the spring to be is 1 Newton per millimeter. So if there is 1 Newton, it stretches by 1 millimeter. So 2.67 Newtons causes an extension of 2.67 millimeters because it is 1 to 1. Over here, if you realize, this is 1 to 1. So the largest extension is experienced by 4 millimeters, which is option A. So that is where this standard case helps you. Okay, and this assumption helps you.